All right, good afternoon, everybody. So, hello, my name is Scott Sellers. I'm a postdoc down at Scripps Institution of Oceanography. I'm going to be talking with you today about a project that we've been working with Cal IT2 and PRP and to develop a way to speed up our pipeline and our analysis framework by harnessing the network technologies and the hardware devices. And in many ways, it's kind of changing the way we are thinking about doing science and how we can organize our data and our workflows to take full advantage of the fact that our data transfer rates are now increasing quite quickly. And so I'm going to talk to you about this project. It has to do with discovering knowledge in large earth science data sets. I'd like to acknowledge my co-authors here at the bottom, and I'll go ahead and jump right in. So I'm going to give you a little bit of a background on the importance of earth science knowledge discovery and also the challenges we face with these large volumetric data sets and how we need to start thinking about ways of better organizing our data so that we can transfer them between multi-institutions to be able to perform the types of analyses that we're moving towards. And this Connect PRP pilot project is really how we're going to try to use the PRP to do just that. And so I'm going to talk to you a little bit about the past, a little bit about where we are now, the present, and the current technologies we're using, and then finally the future as well. And so, and in the end, I'm going to really focus on how you all at CENIC and PRP are changing how we're thinking about doing our science. So the Center for Western Weather and Water Extremes is headed up by Dr. Marty Ralph here at Scripps Institution of Oceanography. We focus on trying to bring 21st century science to understanding our extreme weather and climate variability here in the western U.S. We have very unique challenges such as drought and large-scale flooding, water resources, agriculture, many different aspects of how weather and climate impact our society. And of course, our real core effort at CW3E is to understand atmospheric rivers. And that's a terminology that's gaining more traction in the media, but they're essentially large-scale weather patterns that transport massive amounts of precipitation and water vapor to the continental United States. And so we're looking to understand the dynamics of what causes these to occur, looking at seasonal variability, multi-year variability on why sometimes we have very wet years versus why we've had a 5-year drought where very few atmospheric rivers impacted the western U.S. But we're also building tools to be able to take our climate and weather data and transfer it to stakeholders, decision makers who have to use weather and climate forecasts and hydrologic forecasts to come up with strategies of managing extremes, whether it's flooding, such as some of the challenges they've seen up at Oroville Dam this past year, to drought, where there's not enough water to go around for everybody. We also develop high-resolution numerical weather models. So we have our own in-house custom weather research forecast model that is very high resolution, generates terabytes of data a day if we were to retain all of that information. And so we have many data challenges in transferring this real-time data volume to people who need to use it to make decisions. And then finally, we also work on subseasonal to seasonal forecasting, trying to determine why atmospheric rivers are more abundant in certain time periods than others. And so we'll go into a little bit of that here in a few moments. I'd like to start off with this image. It was taken by the NASA Apollo 17 astronauts traveling to the moon before I was born. But it really kind of puts into context how complex of a system we have here on this planet. You can see the clouds, the oceans, the continents, the deserts, the rainforest, ice caps, and all of these different aspects of the Earth system are interconnected in one way or another. And it's that connection that makes it very challenging to understand how we predict weather or atmospheric rivers, like the one you're seeing here on your screen. And all of these data sets and these modeling products generate huge volumes of data that we're starting to have to try to rethink how we want to organize it so that we can generate animations that can convey the importance of a forecast when one of these might be bearing down on Northern California and they might have to make water resource decisions. But what you're looking at here is an atmospheric river. It's highlighted in this ellipse, and it's this large, massive transport of water vapor. What you're looking at is integrated water vapor. If you took the entire column of the atmosphere and condensed all the water out, it would be the water at the bottom of that bucket, and around 4 inches or 4 centimeters where you see yellow and oranges, and the blue is very dry atmosphere, very little water vapor. And so this is just one variable we want to look at and try to understand atmospheric rivers, but we really have thousands of different earth science variables that are monitored either by ground-based stations, satellites, even numerical climate models that help us take in lots of observations and produce very continuous fields of information. And these are just some of them. You're looking at from temperature to sea level pressure, vorticity, which is rotation in the atmosphere, cloud tops, and these are all just hyperdimensional data that we're now dealing with and having to deal with on a daily basis. And of course, this data is not static. It evolves in time and space, and taking all of these images and creating an animation, you can see how complex of an atmosphere we have. Again, you're looking at that water vapor, so where you see the oranges and reds, you have more abundance of water vapor in the atmosphere. And obviously these are highly dynamic events, highly chaotic. They're tough to really see, well, where does one start or one end? And so that's where we're trying to take these big data approaches and really be able to segment out important information from these huge data volumes. And that takes, of course, the ability to transfer data, but also the ability to segment it and to go through it using computational approaches. And that's just one data set we use, but there's modeling centers around the world who generate similar volumes of data. The NASA product I just showed you is about 15 terabytes in its entirety, and there's over 30 different institutions generating similar volumes of data set to help us understand earth sciences. And so obviously if you had a graduate student who would want to download or compare, let's say 5 of these models, that data volume would of course could take a very long time to bring to your own laptop unless you were on the PRP. And so using all of this data, I want to kind of lay out a little bit of a science question for you all in order to really help emphasize the importance of what you do and why having the ability to transfer these massive volumes give us the possibility to answer some of these questions much faster than the current way we do analysis. And so, why can't we seasonally forecast the weather? I mean, some people say, why can't we just forecast the weather out just a few days? But seasonally, why couldn't we see a drought begin or start or end? Or what caused those the alignment of all of these different variables that made it to where we had very little precipitation over a long stretch? And well, we have lots of different climate phenomena. You have the Atlantic multi-decadal oscillation, the Pacific decadal oscillation. I'm sure most of you have heard of the El Nino Southern Oscillation, or ENSO. And all of these are kind of intertwined in one way or another. And it makes it very challenging to try to pull out one particular phenomena or another. And so we're going to use big data approaches to be able to really untangle this variability by using all of those large volumes to be able to segment out specific features and systems or phenomena that we want to make a connection to whether or not a drought is going to occur or not. And so traditionally what you do is you run simulations. You have a numerical model that is based on our physics and the dynamical equations of motion that we've learned to use in order to predict the weather. And this traditional approach, of course, has gotten us a very long way, but we still can't answer that first question. And so what we've done is we've proposed a machine-assisted learning framework which will restructure these large volumes of data in ways we think that machine learning and artificial intelligence approaches that Tom DeFonte talked about earlier this morning, those types of data structures can be used in that modeling framework. And so this connected algorithm approach is a segmentation approach we developed to try to reduce the size of the data sets so that we can really hone in on what we're looking for in these vast data volumes. And so just to give you a background on why we want to try to segment out these particular phenomena, in our case it's atmospheric rivers. So if you imagine that NASA animation I showed you, there's lots of data that we don't really need in order to do our analysis. We just want to know where the atmospheric rivers are. And so we run a segmentation algorithm that goes in and tracks in space and time those atmospheric rivers. And once those are extracted, we want to store them into a database that we can search. Show me all of the atmospheric rivers that impacted Northern California, in January over the last 10 years. And we can instantly now have a nice subset of that data to where we can then look and see, well, did it, how fast was it moving? How did it cause a flood? And begin to ask all of these science questions. The problem is that this whole framework that you're looking at took really 4 years to develop. From organizing the data, downloading the data, to segmenting the data, to doing the analysis is very time consuming and computationally expensive. And that's because, well, we're adding a dimension of time to all of our objects that we want to track. So atmospheric rivers. You can imagine trying to track every pixel in that animation I showed you in both time and space. And some of them start and end at different times. They interact, they become one. And so this algorithm has to literally keep track of all of these pixels and load into memory lots of data so that it ensures it completes that object. And so what you're looking at here is one of our 4-dimensional objects. This is just one of thousands in our database. And this is an atmospheric river system that impacted California in 2005. Along the z-axis is time. So if you think, you can actually see the motion where this atmospheric river starts in the top left and then propagates to the east where it strikes California. Just to show you what that looks like as an animation, this is that same object propagating towards the western U.S. and our algorithm is able to keep track of all this and say, you know what, this is object number 1. And so we're going to put that object 1 in our database and we can recall it later. And so we just don't want to study one object, we want to study thousands of objects, and not just one variable, but thousands of variables. And so we want to fill up a data matrix where each row here in this matrix is one of those objects. And then we describe each of those objects using features. Its size, its speed, its starting location, its ending location. Did it cause a flood or not? You can think that there's really an infinite amount of features you could add to one of these objects. The Dow Jones Industrial Average was a certain amount for that day, which wouldn't make much sense physically in the atmospheric sciences, but I mean, you see my point. You can add lots of dimensions here so that those machine learning algorithms that now are very good at looking at patterns can help us pull out what's important and what's not. And so that's the whole purpose of this long framework that I've taken 13 minutes to describe. So how does CENIC and PRP fit into all of this? So I mentioned that whole algorithmic framework took 4 years to develop. Well, we've gotten it down to 20 days. And this is saying, I wake up in the morning and I say, I want to really look at this NASA data set. And from that moment, I would have to then download the NASA data set. I'd have to reorganize it in a format that our algorithm can ingest. And then we have to run our algorithm on it, which generates objects. And then I run my characteristic algorithm to generate all the features. And finally, I have that one little data matrix at the end that I can start looking and analyzing for important patterns. But using current technologies, this is 6 months ago before I even knew what CENIC was, or even the PRP. I just simply, from my laptop, did this pipeline. And the NASA data took over 7 days to download. And so it's a slow server, I'm told. And so we wanted to say, well, what can we do to improve this? And so we talked to Cal IT2. And we laid out kind of where we were having big data, pipeline issues, what the problems were with trying to scale this up to thousands of variables. Remember, that was just one variable that took 20 days. And meeting with Dr. Smar and Tom DeFonte and John Graham and others, they basically laid out a series of tools that we could use to help speed this up. Larry asked me, what would you do if I handed you a 1 gig fiber optic cable? And I thought, well, I'll just plug it in my computer and I'd be good to go. And it turns out it's a little bit harder than that. And so, so the PRP and these Fiona machines can actually do a lot of this data transfer of these data volumes that have challenged us for a long time, but also this Kepler workflow that's been developed here at UCSD and the Jupyter notebooks. And then John Graham said, well, why aren't you using a GPU? You could speed up your segmentation algorithm dramatically. And so we're currently working to convert our algorithm to use these very fast GPUs. It seems that my iCloud account can't be connected. All right, there we go. Okay, so what are we going to do now with this PRP kind of framework? And what I did here is I essentially laid out what we're presently doing. So what I showed you was the past. It takes 20 days to do that type of analysis. And presently now we have been harnessing those Fiona boxes. And so the very first thing we did, or really John Graham did, was want to download this data directly to the Fiona. And simply by using the PRP in the Fiona at UCSD, we decided to download the entire 15 terabyte archive instead of just a 2.4 terabyte archive subset. And that only took 2 days and 2 hours. And for that same 2.4 terabytes that I showed you in that previous slide, that would actually take only 8 hours to download. So this is a dramatic improvement to just being able to say, you know, there's a data set that I want to be able to pull and understand and start to analyze and not have to wait 10 days or so to get it. And so taking a closer look at what we're doing, now that that data set is housed on a Fiona, anybody on the PRP with another Fiona can essentially call that data. That data is being mirrored to the entire network. And so that 15 terabytes now, anybody can be able to transfer very quickly. So having this thread server, which John Graham talked about yesterday, layering on top, which is essentially a piece of software that allows you to subset or to select a certain variable or a certain geographical location and be able to pull just that data volume or that data chunk instead of having to grab the entire file. And so now we've developed our algorithm to be able to talk in between these two Fionas. So the Connect algorithm is run at the University of California, Irvine, and they have a Fiona box. And what we've done is that now our Connect algorithm just calls that data from the UCSD Fiona box and then loads it in, does the Connect segmentation, and then provides and sends back the results to our UCSD. And we're still testing this, and we're getting to the point to where now, just yesterday when we ran a speed test, we were passing 1.1 gigabytes in about 2 seconds from each Fiona from this thread server, the Mira data. And for perspective, MATLAB, which is a software package a lot of graduate students use, it took about 19 seconds to load that into memory on my laptop. And so all of a sudden, now the data transfer aspect of our pipeline, which was causing us challenges and latency in doing our research, is beginning to change. It now turns out that the rest of the time that is being spent is our bad coding, not being computer scientists, just using MATLAB and trying our best to work with our servers and our data sets we have. And so it's really our code now that's slowing us down. The network issue, the data transfer, our algorithm can't even run on the data as it comes in. It would have to actually wait for the algorithm to finish before it could call another file. And so that's a really important point. And so where are we going in the future? Well, we hope that once we upgrade our segmentation algorithm to be able to pull in this data faster using a GPU, we will be able to, in essence, develop a Kepler workflow, which I could wake up in the morning and say, you know what, I want to look at a single variable, press one button, and by the end of the day have at least an idea on whether or not it's the right variable or the right data set, instead of having to wait 20 days. And John Graham here has set a benchmark of getting this pipeline down to 20 minutes. And I remember the first time he kind of brought that up to me, deep down I was laughing, and nobody else in the room was. And the more I've been able to work with CalIT2, PRP, and now learning more about CENIC, I believe that within 6 months or so, we will be able to do just this. And so it's quite amazing.
Scott, on voice control.
I'm sorry?
I want you to wake up and say, Alexa.
Oh, Alexa, yes, run object segmentation on NASA temperature data set. All right. No, I like that, Tom. I like that, Tom. Okay, so how is your work changing science? Well, using just the PRP and the Fiona, simply downloading the data from this very slow NASA server sped us up about 4 times just by using the Fiona box alone. No really other optimization, and the slow part is, of course, the NASA server itself. And our findings and our conclusions are going to truly be sped up because of the fact that now the data transfer aspect is kind of being reduced. And it allows us to now quickly get to, is this the right variable we should be looking at for studying atmospheric rivers? Are there any patterns in this data set? And instead of having to wait a long time or 20 days or 13 days, we hope to do this very quickly. And developing these capabilities, we really think is going to advance the rest of our science. So even ocean modeling, you could generate objects and help to transfer data to and from collaborators for generating a better understanding of how the oceans impact the earth sciences or atmospheric rivers. And this pilot project with PRP, it's a multi-investigator, multi-institutional project. We have scientists at UC Irvine, we have scientists here at Scripps and CalIT2, and we have different areas of expertise. We have algorithm development, we have database development, we have machine learning development, and being able to very quickly pass information and data between all of our collaborators is truly moving us forward into really coming and finding our great advances in our research. And of course, just exploring how to bring these techniques and these networks together and to put our analysis and our current research in the context of these workflows that are supported by all of your great work. And so I'll just go ahead and start to move on to the conclusions. And really removing data transfer as a limiting constraint changes everything. It has my thinking of how to develop an experiment to test certain variables or to do machine learning on different data sets is now, I'm thinking about this workflow now. I'm thinking about how I can optimize not just my code to be able to access all of this massive data that now I can pull very quickly, but also how to ask the questions themselves and begin to think about these pipelines before just downloading 2.4 terabytes of NASA data and waiting for 10 days. And so it's now really time for us to do our part because like I said, it's our code that's slowing us down. And so now that network speed is there, we have to engage our community and your community to try to work together to learn from one another in order to help move forward science. So with that, I will, I think, take some questions if there's time. And yes?
Yeah, so how you said that the slow part was the NASA server.
Mm-hmm.
So how were you able to accelerate so much if the NASA server was still very slow? So I didn't get that.
John?
He was originally downloading it to a laptop that was not optimized for data transfer. And so when we moved his download function over to a Fiona that is optimized for download, we were then able to achieve the maximum output that the NASA server could generate.
Okay, thank you.
They also limit me, I could destroy their server if I did parallel gets from it. And so they said no more than 4 at a time, please.
Okay.
You're a one-man denial of service attack. Any other questions?
I didn't have a question, but I just wanted to commend you. This was incredibly clear and very, very inspiring. And as a non-technical person, for you to be able to communicate this to me, the meaning of it, it's pretty impressive. So thank you.
Thank you very much.
So Scott, I couldn't agree more with the comment that was just made. And to the audience, I'd say Scott is an example of a found scientist who we didn't bring to the party. I mean, he was not in the PRP proposal. And what was not maybe so clear is that he was at Irvine in Sarusian's group that has all of the global participation that goes on in real time monitoring. He's a very well-known person in atmospheric sciences, and so then when he came here to work with Marty Ralph, who's another very famous scientist in water at Scripps Institution Oceanographer, he became the perfect glue person between two institutions and two world-class long-term science projects, and you can just see his enthusiasm and you know how he's been able to take advantage of this. Well, we're in year 1.5 of the PRP of a 5-year project, and so my great hope is that we are going to find a number of other Scott Sellers in other fields that over the next couple of years that will take advantage of what we're offering to them and give us an explanation, not in terms of networking, but just building on the incredible networking engineering that CENIC and the network community and the university, all the campuses provide, for how it changes their science. And that's one reason we wanted to bring it to you, because we actually don't have that many people who can do what he's just done in the whole state at this point in time.
Actually, I have a question, but maybe not for you. How do we now infect NASA with these Fiona boxes?
Okay. I got a sad story to tell you. I served on the highest level NASA advisory committee to the NASA administrator for 4 NASA administrators. And I spent 3 years, 5 years being the head of the subcommittee of that on all of the IT and telecom activities in NASA. And I visited all of the NASA centers. And I have spent at least 10 to 15 years presenting this sort of stuff, going all the way back to the Optoputer, to NASA, to try to get the natural layout of the NASA centers, as like we do campuses on CENIC, and working, you know, all the way up to the NASA administrator and with all of the center directors. And I got to say, I got squat to show for results.
Didn't they agree to standardize on WordPerfect 1.0? Oh, no, that was an IH. That's right. That was an IH.
Okay, last question maybe.
Hi, my name is John Gillespie from the University of Missouri System. So when you think about the kind of processing that you're going to need to be able to do as you expand the amount of data that you attempt to process, how do you start to quantify that from a technology perspective, and how do the technologists help you?
Sure. So one challenge about these types of data sets is that each data volume can have 20 or 30 variables, not just different types of variables like precipitation or temperature, but also at different levels. So in the atmosphere, different pressure levels going all the way up to the top of the troposphere. And trying to figure out a way to where all of those different variables aren't overlapping in the data sets. Because I mentioned that we pulled one 15 terabyte archive, which has roughly 20 variables. But there are about 12 other archives from NASA who have other variables. And so, trying to figure out, is there a place that we can store all of those, making sure that they're all in a similar format, which they should be, and then being able to have rapid access to them. Because, in theory, what we would like to do, at least with the Connect algorithm, is have all these archives kind of lined up and then just either go through each variable at a time, or now that we will hopefully have a GPU doing this process, and we can do 15 or 20 variables at a time, and essentially go through and at each level in the atmosphere for each variable construct these objects so that we can try to determine which, let's say, altitude is a pressure anomaly the most important for an atmospheric river to develop, or what type of environment assisted in a hurricane to develop. And so having at least the ability to be able to do all of that on the data sets that are available and that are constantly coming out, and even some more real-time products generate terabytes of data a day, and most of that data is just thrown away because it's only, let's say, the precipitation field that it needs. And so ensuring that we have the storage, and of course these Fiona have flash storage, so it's fast. I think that our algorithms will be able to take advantage of that. But making sure that that's available, or how best to structure that data management is another challenge that I'm not entirely sure we have an answer for, because there are many different data volumes with many different variables, and this approach really wants to use all of them. And it's how do you actually do that? Because in the past I have to be very selective. I want one variable to look at, and then go through the process of the analysis, and in the end either, oh hey look, it's an interesting pattern and I'll publish, or not. Okay, well we have to kind of start over. And so hopefully at some point we'll have all of these objects created and stored in a database, to where then it's just a matter of doing the analysis to really discover the knowledge that's contained in it.
Okay, let's thank our speaker.